Start. Okay, share screen, share screen. Beautiful. Okay. All right. Hold on. All right, so I'm working off my iPad, so if anybody has a question, please feel free to mute yourself again, because I can't see what's in the chat. And by the time you ask your question, it's going to be too late. Hold on. Let's wait till everybody joins. Okay, so we're going to start off with a couple of questions from chapter 5. Basically, there's just going to be relationship questions. One sec. Okay, so I'm going to start off with a couple warm-up questions, see how you guys feel, and then we're going to go into a little bit more difficult questions. All right, so how do we go about these questions? You're going to get something along the lines of like, which of these terms best describes these pair of compounds? Are they enantiomers? Are they diastereomers? Are they constitutional isomers? Are they the same compound? Are they different compounds? How would we go about that? Does anybody have an idea what we would do first? In this case, in the first case, in case A, how would we go about knowing the relationship? You can speak up. You can unmute yourself. Anybody have any ideas? Okay, if you're completely lost, first thing you would have to recognize is that they have the same amount of carbons or the same amount of heteroatoms. So here we have how many heteroatoms? We have 1, 2, 3, 4, or how many carbons rather? 1, 2, 3, 4, 5, 6, and 2 heteroatoms. Those heteroatoms being iodine and chlorine. So let's look over here. Same situation. 1, 2, 3, 4, 5. But we still have the same heteroatoms. Are these constitutional isomers, diastereomers, same compounds, diastereomers, enantiomers? What? It's obviously if they have a different molecular formula, they would be different compounds, right? So that's an easy way, just like we found out like the constitutional isomer question a couple like the last week or the week before. That's all you have to do. Okay, so same situation here. All right, here I can tell you right off the bat we have the same number of carbons. This is 6, all this is 6, right? This would make it 7. Again, 6 and 7, so we have the same amount of carbons. So what's different? What do you call this? They have the same molecular formula, but what's off?
Where the bromine is located?
Right. It's not located on the ring. Here you could tell it's located on the ring, right? But this is not. This is located on a methyl, on an SN2 group. So since it's not located on the ring, it's located in CH2 group and in methylene group. We know that these are constitutional.
You guys can turn the heat up if you're cold. I turned it down earlier because it was so hot. Oh, really? Yeah.
Brett, can you help me with?
Can you mute yourself?
For Madeline Yager.
Printing on.
Hey.
Blood requisition form?
Yeah.
Hey.
She's on schedule for today.
Yeah, the mom is, and she said she lost it. Oh, she didn't get the.
Oh, what's the account number?
The blood work like now.
Okay, sorry about that, guys. Okay, back to relationship questions. How about here? How would you go about doing this? So from the get-go, they look like they have the same amount of carbons and they have the same amount of heteroatoms. How would I go about this? Like, what do I need to do? What makes sense? Anyway, what would be my next step? Okay, I determined that they have the same amount of carbons and heteroatoms. They seem to be connected in the same manner. This almost looks like a ring flip, right? How can we confirm?
You could do an actual ring flip and see if it's the same.
Okay, I could. I also, so if I did a ring flip, sure, but just speaking in more general, this is a ring flip would work, because then this would be, let's see, if this is pointing axial up, then it would be pointing in the same direction. This is the worst ring flip. This would be now pointing equatorial, pointing up. And then this BR, since it's pointing equatorial up, it's now going to be pointing equatorial, Jesus. It's going to be pointing axial up. Axial up, right? Same goes for this methyl group. Methyl on carbon 1 was pointing equatorial down. Now it's going to be pointing, well, technically it was pointing equatorial down, but still, when you draw these, this technically would be in the axial position. It wouldn't be drawn like this. Still, we're, okay, so this is going to be axial pointing down. And on carbon number 2, this would be equatorial pointing down, right? But does that look like our molecule over here?
No.
No. Okay. So what's another option? I mean, a ring flip is a good idea, but what's another option? This is all of chapter 5, guys. We could assign, right? Could we not assign because these are 2 chiral centers? Right? Let me use a different color.
Again, the ones that you just marked in green, what are they again?
Chiral centers.
Okay, yeah.
Yeah, so actually let me conserve the same coloring. So this is a chiral center, this is a chiral center. Okay, so now that we have the 2 chiral centers identified, we could just simply, you know, assign chirality. And I'll let you guys tell me what's the stereochemistry on the carbon in green. Is that R or S? Are you guys familiar? This is an easy way to go about this. You just look at chlorine. That would be 1. This would be 2. This would be 3. This would be 4. What is that?
R.
B R. Correct.
R.
Same situation. Let's do it in red down here. Bromine would be 1. This up here would be 2. This would be 3. This would be 4. What is that? S, right? So you have carbon green being a stereoconfiguration of R, absolute stereoconfiguration, and carbon red of S. Let's do the same thing over here. I'll just tell you, just because, you know, if you did 1, 2, 3, 4, this should be obvious to you that this would be S. And if we did here 1, 2, 3, 4, this should be obvious to you as well. What is this? This looks like it's S, but it's actually R. R, correct. Hold on. So since these are both, look at the green carbon, they're both R. Look at the red carbon, they're both S. This is simply not a ring flip in the way that you've learned, like we did at the bottom, but it's a ring flip that is a vertical ring flip. All I'm doing to the molecule is flipping it this way, essentially. Does everybody see that?
Yes.
Okay, so if you get a question, you know, where you have, I don't know, something like this, just a simple, okay, maybe something a little bit more, something like that. And I told you now that this molecule now looks like, one second. And I'm telling you now this molecule would look like this. This is not, it's an enantiomer. What would it be? It's just a simple molecule flip, right? You're going to either look at this as flipping down or flipping up. Okay, so what would these be? This is the same compound.
So would it be identical?
Yes, it's the same compound. I just flipped it. And you guys should be able to visualize this in your head. If not, bring your molecular modeling kit, or just like kind of use an object that you're familiar with, your hand or a water bottle, and see if, okay, if I had, you know, chlorine pointing out of the water bottle pointing up, if I flip that vertically, or if I flip that horizontally, is that now is it the same compound? Is it an enantiomer? You know, like just think of it, you know, in the 3-dimensional space. Okay. Okay, let me do another question. Actually, I had one more question. Where'd it go? I had another question. I guess this one is fine. Okay, so now this question. These two, what's the relationship between these two? And can anybody tell me why? So let's start with
Is the one,
let's do the
So-
second one first. Tell me what's the second one. And the way I drew it should be obvious. So this is relating back to the previous question.
is it just an enantiomer of the original? It's just been flipped?
No, the second one,
It's the same compound?
yes, ma'am. The same compound, because we're just flipping horizontally now. Do you see what I'm saying? We're flipping this as if this was the right side and this is the left side. And you can see hydrogen is still pointing up and chlorine is still pointing down. And you can see it's a little wonky, you know, little molecule. And that wonky little molecule, I'm now looking at basically from the back side. If this was the front, now I'm looking at it from the back. Does everybody see that?
Can you explain that one more time?
Okay, so here, what gives it away, first of all, is it's the way it kind of looks. This doesn't look like a perfect square, or half a square rather. Or sort of looks, it looks like a half square, right? And if you can imagine as this as the front, this is the right side, this is the left side of the molecule. It's just imagining. Look now here, that's right side. This is the right side of the original molecule. We're just looking at it from the back. And this is the left side. And we can tell because hydrogen is still pointing up in basically an endo-exo preference. And chlorine is still pointing down, basically in what we call an endo preference. Chlorine is pointing up and hydrogen is pointing up, chlorine is pointing down. This was just a simple horizontal flip. or vertical flip rather. I think this is what we call vertical flips. Okay. Good. Did that make sense? Did
Yeah.
that answer your question? Okay. What about this one? So we know that this is the same compound. How about for the first structure? Any ideas?
Are we comparing the first one to the left to the one to the
Yes,
one
we're comparing the original with another compound. Or is it another compound?
they look the same except that hydrogen and chlorine are flipped.
Right. So how would you go about answering this question? Think about it. We determined that it has the same what is it? The same number of carbons, same number of hydrogens, same number of heteroatoms. But how would we, what was the third method? Chapter 5. What was the third method? Excuse me? We would assign, right?
Yeah, assigning the chiral centers.
Yeah, okay. So how would we assign this? Let's assign carbon, this carbon, and this carbon. But here's a reasoning strategy. Whatever chirality center is in pink, whatever it is, whether that be, I don't know, in this case, it's probably going to be S, I believe. If this was S, this can't be S, right? This has to be R, just based on the position of the chlorine, right? They look as if they were what? If something is S and the other one is R, what do we call that relationship?
Enantiomers?
Yes, they're called enantiomers. Okay, but is this an enantiomer? And can anybody explain why or why not? Nobody knows? Okay. Do we have more chiral centers in this molecule?
No.
No? Are you sure?
Well, the bridgeheads can't be, right?
Yes, they can.
Oh,
They can be chiral centers. The bridgehead carbons, in fact, are chiral centers. We usually don't recognize them as chiral centers, but they are, and they have a configuration. Okay? And in this case, it'd probably be 1, 2, 3, 4, 1, 2, 3, 4. So this would probably be, I think these are both S. It doesn't matter, but you would recognize that these, if they have the same, like nothing's changed with these two chiral centers, right? These two chiral centers remain having the same configuration. I didn't flip the molecule. I haven't really changed any other substituents on this molecule. I only changed the chiral center in pink. So if you have something along the lines of, let's say you have multiple chiral centers, as we do in this case, and we have at chiral center 1 and at chiral center 2, we have a configuration of SS, and in chiral center number 3, we have a configuration of S, and in the other compound, we have a chiral center. We have chiral center number 1 staying the same, chiral center number 2 staying the same, but now at chiral center number 3, we've changed it to R. What do we call that when we only have, so they're not complete opposites to each other. Not like your hands, they're not complete opposites to each other. They just have one chiral center that differs in configuration. What do we call that?
stereoisomer?
No, not stereoisomer, because that's the umbrella term. Starts with a dia, ends with a stereo.
Diastereomer.
There you go. It's a diastereomer. So these are diastereomers. Okay. So watch out for that. We may not ask you a bicyclo because that may be a little bit tricky, but do recall what the definition of a stereoisomer is. Or if you get configurations that only differ in the last or one of the chiral centers, then you will know that it's a diastereomer. Fair enough? All right, let's move on. Okay, how about this question? Fisher projection in Newman. Ugh, ugly, I know. But we can figure this out. How would we figure this out?
We could draw the Fisher projection as a Newman.
You could draw the Fisher projection as a Newman. You don't have to. If you feel more comfortable that way, be my guest. I honestly don't feel that comfortable drawing Fisher projections as Newmans. Also, we can just go back to assigning. When in doubt, you can always assign. And so if we assigned, let's do chlorine in green and bromine in pink. Okay, so if we assign the first carbon, the first stereocenter or chirocenter, we're going to get, just for the sake of quickness, we're going to get R. And for the second stereocenter, we're going to get S, right? Not too bad. How about for the Newman projection? Are you guys comfortable assigning configurations with Newman projections? If not, honestly, I wasn't either. So every single time when I did one of these questions, I always drew them into bond line structures. And so the biggest tip is drawing into bond line structures. This is what we did a couple classes ago. You can draw this to a bond line structure simply by twisting it, right? What you're seeing here is basically as if we twist this molecule 60 degrees to our left, right? So if I drew this, this would be basically my top heteroatom. This would be my bottom heteroatom. Whatever is on my left would be, it's not always the case because I could easily be looking from the other side, right? But in this case, I'm assuming that I'm looking from basically what is carbon number 1 and carbon number 2, or technically this would be carbon number 2 and carbon number 3. I don't know. But if I was looking at it from the other side, what you've been taught in class and what's usually in the book. So on top, I'll draw it like this. This is going to be bromine. This is the carbon. Here's another carbon. And this is chlorine, right? So on the first carbon, on our Mercedes-Benz logo at the beginning, at the front carbon, this would technically be carbon number 2, but whatever. At this carbon right here, not the back carbon, at the front carbon, on the left, again, this would be wedged. And on the right, this would be, or sorry, on the left is dashed, on the right is wedged. So on the left, we would have what? A methyl group, right? This is a methyl group. Okay. What about here? This would be our alcohol or hydroxyl. Same thing on the back carbon. This would be our methyl. And this would be our hydroxyl. Cool? Cool. So we can immediately say that these have the same amount of carbons, have the same amount of hydrogens, have the same amount of heteroatoms, and they are connected the same. It's bromine, methyl, alcohol, and methyl alcohol chlorine on both stereocenters, right? Okay, so now all we have to do is assign. So chlorine in green, bromine in pink. What is the configuration at the pink carbon, bromine.
S.
S, right? I hope everybody saw that. 1, 2, 3, 4. That would be S, right? How about the back carbon?
S.
S as well. 1, 2, wait, let's do this in green. 1, that's the 2, 3, 4, right? Actually, this would be 2. Hold on. No, that's 2. 3, Jesus. Also S, right? So if this is SS, let's do this in same color. So this is SS and this is RS. What's the relationship? Look at this example.
Diastereomers?
Diastereomers.
Exactly, diastereomers. So these are diastereomers. Okay, so rule of thumb, first count your carbons, then see if they have the same connectivity. Look out for any kind of horizontal or ring or vertical flips, and then assign configuration. Okay.
Can you just repeat the steps one more time? Like I'm just writing it down, making sure. So I know you
Sure.
said count your carbon.
So the first thing is count the number of carbons, hydrogens, and heteroatoms. The second step is see if they have the same connectivity. To see if that bromine is attached to the carbon that's on the ring or if it's attached to some substituent. That's the connectivity. That's how you can tell it's constitutional isomers. The next step is looking out horizontal. Hold on. The next step is looking out for horizontal flips, or in this case, vertical flips, in this case over here. And the last step, and this is like the foolproof method, is assigning configuration.
Okay.
Okay?
Thank you.
You're very welcome. All right. So now let's identify different patterns. Okay, this is straight from your textbook. You're gonna get a question like this. What would you put for the first step? What is this? Is this loss of the leaving group? Is this rearrangement? Is this proton transfer? What is this? Step 1.
The SN2.
Not reaction. Just think chapter 6.
Nucleophilic attack?
Yes, nucleophilic attack. Easy, nucleophilic attack. What's the next step?
Loss of leaving group.
Yes, ma'am. Loss of leaving group. Okay. What's next?
Nucleophilic attack.
Same thing, nucleophilic attack. And final step.
Proton transfer.
Exactly. Proton transfer. Easy. And if you guys are curious, this is just a simple Grignard mechanism. You'll learn this in chapter 12. So this is Grignard. This is the Grignard mechanism. Where this is our Grignard reagent. This chlorine is obviously our leaving group. And so we're adding 2 Grignards. And this is usually followed up as a second step as water. So Grignard is usually labeled RMGBr, something like that. So the R group is our substituent, which is being added to the electrophilic carbonyl carbon position. Okay, but you'll get into that next week. Okay, but this is just a preview. Here, this is what we call hemiacetyls, acetals, whatever, or an acetyl mechanism. Okay, but let's identify the steps because that's not important right now. And this is in Orgo 2, so it doesn't matter. You don't need to learn this. Okay, what's the first step? There's a lot of steps. First step,
Proton transfer.
protonating that oxygen, right? Proton transfer. Okay, second step. Second step.
Nucleophile attack.
Yep, nucleophilic attack. We're attacking with an alkoxide ion. Okay, here we're deprotonating that alkoxide ion, so this is also considered a proton transfer, right? Proton transfer here. Another proton transfer, right? Sometimes in chemistry, we abbreviate these two steps as an internal proton transfer. You might not see that until Orgo 2 because you probably won't be doing that many mechanisms in Orgo 1, but you'll definitely see in Orgo 2. So this is just a shortcut of writing these two steps, or trading this proton and putting it on here. Okay, but that's not important right now. But it's just so you have this in your mind. All right, here, what's happening?
Rearrangement.
Is this a rearrangement? Notice you've created a good, what do we call this?
No, it's leaving group.
Yes, we created a good leaving group. So this step here is loss of a leaving group. Okay. All right, final two steps. You have another alkoxide ion. Oh, this way.
Nucleophile attack.
Yep, nucleophile attack. And last step, this is just simple
Proton transfer.
There you go. So we expect you guys not only to do mechanisms, but identify the steps in these mechanisms, because it's only 4. Which ones in these 2 did we not do?
Rearrangement.
Exactly. So we have nucleophilic attack, loss of a leaving group, proton transfer, but we didn't have any rearrangement. But you'll have plenty of rearrangement in your equations. So just know that those are your 4 basic steps. That's as simple as mechanisms can get, is just identifying whether it's a proton transfer, a nucleophilic attack, a rearrangement, or a loss of a leaving group. It's those 4 steps. If you're doing something else, you know that you've done something wrong, okay? So here is a reaction coordinate. And this is chapter 6. This is just helping you identify. Oh, by the way, I don't know if anybody has picked up on the little titles that I've given these. They're song lyrics because I'm lame and I wanted to make this fun for myself.
No, they're great.
Yeah, I mean, nobody has gotten them because I don't know if,
No.
Maybe, does anybody know the what song this is from?
Is it Ciara song, right?
Yes, thank you. Good job. What's up, ATL? Okay, so yeah. All right, let me see you 1-2 step. I want to ask you how many intermediates, how many transition states, and how many steps. Let me see you 1-2 step. How many steps are in this reaction coordinate? PE stands for potential energy. So you can also see that as kilojoules per mole. So how about, how do we go about this? Do you guys remember chapter 6 or yawn, or what are
do we kind of step based off of the transition state or the intermediate?
Both. I mean, what is my intermediate and what is my transition state?
Your intermediate is the trough and the transition is the peak.
Yes. So to not use like wave mechanic terms or whatever. So these little points are the transition states and these are the intermediates, right? So
Question before you continue.
yes, ma'am.
So when it's up, you said it's potential. When it's down, it's intermediate.
No, when it's these peaks
Yeah.
represent transition states. Transition states. Okay. And this little symbol is how we denote transition states. These little valleys, you know, these momentarily stabilized compounds are what we call intermediates. Okay.
So the
And
transition is like the peak.
yes, because it's
And
higher.
Okay,
It
yeah.
represents, you know, I don't know if you guys remember, it represents like a carbon, and we said that carbon doesn't have 5 bonds. But what's happening here is that, let's say you had some kind of SN2 reaction, you had like, I don't know, this is a methyl, let's put this, you know, in the plane, this would be called an ethyl, and there's a bond that's forming and there's a bond that's breaking, right? If we said that, I don't know, Br is attacking and iodine is leaving, and we have what we call SN2 inversion of configuration, and this has slightly negative charge, slightly positive charge, slightly negative charge. This is straight from your book, and it's denoted something like this. This is the transition state. That's what these transition states are representing, is that you're having, you know, this nucleophile coming in to carbon at the same time as this loss of the leaving group, right? That's what this represents. Okay. So those are the transition states.
Okay.
And these intermediates are just, you know, it's a 4 bonded carbon, but it's representing, you know, somewhere in between. It could be representing like this, like before rearrangement. Let's say if you had something, I don't know, along the lines of like something like this, you know, this would be an intermediate because the next step may be something like this, where you have a methyl shift, right? So this would be considered your intermediate. Okay, and this is, I mean, we don't usually put asterisks, but this can be considered your asterisk intermediate. Okay, and so again, let me see you 1-2 step. How many steps is this? We've already identified we have 3 transition states and 2 intermediates, and this is our reactant and this is our product. So okay, this is a favorable reaction. Cool, don't need to know that. How many steps?
5.
How did you get 5?
Would you count the transition state and intermediate states as steps, or?
No, because when we have one reaction, when we have like a single SN2 reaction, and the only difference between SN1 and SN2 is that one is concerted, this is concerted, and this is stepwise, right? And what concerted means is that it happens in a single, like what a single transition state, like we did here. And this would probably be an SN2 reaction. And this, an SN1, if I had some, you know, now if I had like bromine attacking here, this is what we would consider a stepwise reaction, right? And so how many steps are in a concerted reaction, like an SN2 reaction? How many steps? It happens at the same time, right?
It'd just be one?
It would be one. Yeah, one step. my former professor Salome used to describe this. You're buying something from like a corner deli or like anything. Like you pay cash up front immediately. And stepwise, he described it as like buying something online where you pay for it first and then it comes in the mail like a couple of days later, like 2 day shipping. So you can remember that like as immediate transactions or as like pay now and then receive later. So this is at least stepwise would be at least 2 steps. Okay. So having that in mind, how many transition states are in a concerted, not a concerted mechanism, a concerted reaction, a concerted SN2 reaction? How many transition states? Think about it. SN2, how many transition states? Look here. Okay, so it's just one transition state, okay? And there wouldn't be an intermediate. This wouldn't be considered an intermediate. So this would be just one transition state. And how about in stepwise? Well, with that logic, we know that there's at least 2 transition states and 1 intermediate. Okay? That is all fine and good. This is just telling you what the definition of this is. So if we look at this reaction, how we can look at this is basically, okay, intermediate step or transition state plus intermediate equals 1, basically one step. Here, another step. Here, another step.
So
do we all see that?
3 steps in total?
Yes. This has 3 steps. Has 3 steps, 3 transition states, and 2 intermediates. So again, last thing to summarize. When you're given something like this, you look at the peaks. Those peaks or troughs represent transition states. Those valleys represent intermediates. And every one of these from product, if we could call this just product and reactant, reactant and product, that would just be 1 step. Yeah. Product and reactant, or reactant and product. That would be just 1 step. So again, 1 step, 1 step, 1 step. So this has 3 steps, okay? So this should be called, let me see, 1, 2, 3 step, but doesn't matter. Okay, cool. All right. Okay, another fun lyrics. What's the lyric to that? What song is that? Does anybody know who sings it? Anybody? Anybody at all?
The single ladies, right?
Beyonce.
Yeah, there you go. All right, just making sure you guys are still paying attention. Okay, single ladies. All right, single ladies. What am I doing? I'm drawing this mechanism. And I just gave you a big hint. I'm putting a ring on it because I like mechanisms, right? So what's the first step? Let's think of chapter 6. Let's think of identifying patterns. What do we call this? Well, so we have a pair of electrons, and hydronium can be seen. You could draw a hydronium like this, right? And we can see this as a source of protons. This is a source of protons. Okay, so what are we going to do? Notice in my final product, I don't have an alcohol. No alcohol. Okay.
Are we
But I
gonna do a
still
proton
have-
transfer and then leaving group?
Yes, sir. We're going to make this into a good leaving group. Cool. Now let me redraw that. Boom, 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 boom. Good leaving group, right? So that was the first step. The first step was proton transfer, PT. You don't have to write it. Sometimes they just put this in the mechanism, but this is proton transfer. Okay, what's next? What's happening next? Loss of a leaving group, right? Like you just said. So loss of a leaving group. So basically, water now leaves. This is loss of a leaving group. Okay, so water leaves. Water is now leaving. So if water leaves, what's happening? And actually, let me do you a favor so you can see this a little bit clearer. I'm gonna
Do we have
that.
do we have like a nucleophile attack sort of thing, but within the mechanism or within the compound?
Yeah.
From the pi bond?
Good eye. Good eye. All right. Now, where do I have a nucleophilic source on this compound?
Yeah, the pi bond.
Good job. So pi bond. So this would be a nucleophilic attack, right? So this is a nucleophilic attack. And how am I attacking this? So like, what do you mean by attacking this? Like, like help me understand. So you're saying that I can take these electrons, right? And I can basically connect them here at this carbon. Correct?
Yeah.
Yeah. All right. And that it's getting closer to our product. That seems right. All right. Let me draw this. Okay. Hold on. Boom. And I'm going to draw that bond that we just made in pink from that alkene. Okay, cool. All right. Am I missing something?
The pi bond, sorry, the bond in the middle?
No, that bond in the middle, that was the alkene. That was our source of electrons. That was what was nucleophilic attacking. What made that nucleophilic attack was the alkene.
Is it the pi bond? Sorry, your thing is covering the product, so I can't really see. Up top.
Can you zoom out a little bit?
Oh, sorry.
Yeah, it's the pi bond?
No, the pi bond is what's attacking. The pi bond is basically a source of electrons. It's a source of electron density. Remember, nucleophiles are a source of electron density. All we didn't change the number of carbons. We just put the electrons that were here that I drew in pink here, right? Here and here. I put them connecting this carbon, let's say this carbon in green or in orange and this carbon in green. But am I missing something? Is this the correct structure?
Is it the charge?
Excuse me?
The charge.
The charge, yes, correct. So where am I placing that charge?
The double bond.
Be more specific. It was at the location of the double bond. You are right. So it was here.
Positive charge.
It was here. It was a positive charge, but where it does go here somewhere. But does it go on this carbon or does it go on this carbon in green?
The top carbon?
How do you know that? You're
There's
right.
a proton on the bottom one.
Oh, yeah.
Yes, exactly. Because this one had a hydrogen, right? That's an implied hydrogen. Here, up top, did it have an implied hydrogen? Let's count the groups. It would be 1, 2, and this represents the 3 and 4, right? Think about it in an alkene sense. Does this carbon in gray have any implied hydrogens?
No.
No, exactly. And once it loses that pi bond, so it didn't have any implied hydrogens to begin with, so what would the charge be? It would be positive. Got it? So that's where the positive charge goes. And we're almost there. We're almost there. So that's just let me make that into a thought bubble. Okay. So we're almost there. Actually, let me expand on this. So whoever is watching the recording or just sees my notes later notices what's going on. Thought bubble, thought bubble. Okay. So now here, we're almost to our product. What do we have to do next? We're reforming this alkene, right? This alkene, we're reforming it. How are we reforming that alkene? And Joseph, you alluded to a very important part. That bottom carbon still has a hydrogen, right? And think about it. This is a catalyzed mechanism. What I mean by catalyzed mechanism is that this hydronium gets reproduced. So if I, in the first step, I had hydronium, and then I made water by deprotonating hydronium, can't I remake hydronium somehow by what we call a proton transfer, correct? Right? We're going to remake that hydronium with water. So what would you call this step? So you have water. You draw water.
So we're doing a proton transfer from that bottom middle carbon to the water molecule.
Yes.
And then we form a pi bond between the two center carbons.
Yes, because the electrons between this carbon in green and this hydrogen are now heterolytically cleaved, and they're placed now between that green carbon and that positive charge. So now these electrons push up here, reforming our alkene. So they want transfer from water, right? And now we've reformed our alkene. Does that look like our product? Yes. Okay. So I know it might seem like a lot, but if you notice, it's the same kind of, steps: proton transfer, loss of a leaving group, nucleophilic attack, proton transfer, and we're done. Really, it's just 4 steps. Okay. So not too bad. We pronated the alcohol to make it a good leaving group. Okay. That was this first step. That good leaving group now left. All right, leaving us with a secondary carbocation. That secondary carbocation was resolved by nucleophilic attacking it with the alkene. That's what is showing in pink, right? That's what's representing our nucleophilic attack. Those electrons now form this pentane ring, but because we got rid of the alkene, the carbon on top, which I showed you guys over here, that let's say that was the gray carbon, now has a positive charge. And to get rid of that positive charge, we depronate this molecule. So we're depronating this molecule, deprotonating. I'm just going to abbreviate. Deprotonating this molecule, and we're protonating water because we're reforming hydronium one more time. Okay, so we're reforming hydronium, and that also makes our alkene because those electrons between the green carbon and the gray hydrogen are now being donated to this to make this alkene. Okay, is everyone clear? Yes, no, maybe so.
Yes.
Yes, thank you. Okay, perfect. Now, one more. You see, I didn't want a 4-carat ring. I wanted a 5-carat ring, you know, because I really like mechanisms. What am I doing here? Okay, so notice the difference between the first mechanism and the second mechanism. The first mechanism, we got rid of water, right? In this case, we're adding water and we're getting rid of an alkene. That should give you a hint. So what's the first step? You have A, B, C, or D. Proton transfer, nucleophilic attack, loss of a leaving group, or rearrangement. What's the first step?
Would it be nucleophilic attack?
Yes, what are we attacking? So how are we attacking, rather? So if this is hydronium, and I told you hydronium is a source of protons. This is hydronium. What am I nucleophilic attacking? Like, what am I? This technically wouldn't be considered a nucleophilic attack, but it does seem like a nucleophilic attack. What's happening? Where is my source of electron density? We did it in this example. What was our source of electron density? The alkene, right? That was the source of electron density. Here we have an alkene. It's a source of electron density. And what we're doing is basically saturating that alkene. And if I saturate this alkene, I'm basically saying that I'm picking up one of these protons, right? I'm picking up one of those protons. Okay, cool. I'm picking up one of those protons. Where is my positive charge now? And also, where would I have placed that proton? Would I have placed it here, or that hydrogen? Would I have placed it here or here? So 1 or 2, where would I have placed that hydrogen? Somebody speak up. Where do I place that hydrogen? At position 1 or at position 2? Think about stability. What would be more stable? A primary carbocation or a secondary carbocation? Because I only have 1 hydrogen. So if I place it at 2,
Secondary.
1, yes, exactly. If I place it at 1, I would have a primary carbocation, and that's unstable. So if I place it at 2, at position number 2, I form a secondary carbocation, right?
I have a question.
Yes, ma'am.
So for it to be stable, it should be on the secondary carbocation.
Yes.
Okay, so that means primary is more weaker. It's unstable.
Very unstable. Yes.
Okay.
In fact, usually when you have a primary carbocation, you have it happens, it's a kinetic debate. It happens so quickly that you have a hydride shift. So even if I did, let's say I did place it here, in chemistry, what you will see if you have this primary carbocation is that you wouldn't be able to isolate this compound. Usually what would happen is that the same compound would hydride shift. This is what we call hydride shift, and would then place the hydrogen on the other side. It would place it here, and it would form a secondary carbocation.
Okay.
But that's just, that's chemistry for you. So, all right, we know that we're placing it on the right-hand side, okay, here. We know that we're placing it here, okay? And I'm not going to draw this because then it's going to confuse you guys, but we know we placed it at the secondary position, okay? But I will draw the secondary carbocation because this is important. What's happening? So this was proton transfer, right? This is a proton transfer. What's happening now? Look at our structure. Okay. What do you guys think is happening? Somehow we're making something like this. Is this a methyl group that we're making? Interesting, right? We're not alkylating this compound, but somehow we're making a methyl group. And also, besides making a methyl group, we went from a 4-membered ring to a 5-membered ring, right? So somehow we have to, break this ring and reform it. How are we going to break and reform that ring? I'll give you a hint. It starts with a re, ends with a arrangement.
Rearrangement.
Yes. And what are we rearranging? What bond are we rearranging?
Is it the bond connecting the third carbon in the last one? In the ring?
So I'm going to point. Is it this bond? Is it this bond? Is it this bond? Or is it this bond?
The first one?
Yes, ma'am. It's the first one. So this bond here is going to break and is going to be reformed here. Okay, I'll do that one more time. This bond, this bond in pink is breaking and reforming here. Okay, this is what kind of step? Rearrangement, right? This is a rearrangement step. And if we count, now we have 1, 2, 3, 4, 5. Did we not just go from a 4-membered ring to a 5-membered ring? Yes. Okay. And now, so what's happening? So for the people that are going to be watching, I'm going to erase this here, make this like that, and then show that this is breaking and it's reforming here. Okay. So now I have this pentane ring. What was that carbon number 1? Look at carbon number 1 now. What do you call this group?
Methyl.
Kind of methyl. Yes. Cool. Whoops. Methyl. On carbon number 2, there's also a methyl. But am I missing something?
Charge.
Where?
At the top.
Here? Does that look right?
No, it's the next one over.
Yes. Why? Because we broke what was originally the bond between, let's call this 2, and originally this was 4, but carbon 2 and carbon 5. We're breaking that bond. So this bond no longer exists. This doesn't, carbon number 2 doesn't have implied hydrogens, right? So it only has 3 groups. So it would be the positive charge on that second carbon. 1, 2, 3, 4, 5. Okay. All right, we're very close to our product. What do we need to do now? We're adding an alcohol, right? How do we add an alcohol? We haven't gotten to that chapter, but we do know the 4 steps: proton transfer, rearrangement, loss of a leaving group, and nucleophilic attack. So if I'm going to nucleophilic attack this, what am I nucleophilic attacking it with?
Water.
Water?
Yes, you guys are correct. Water. Okay. And this is what I mean by it, like it reforms, you know, water, hydronium, whatever. And also there's lots of water and hydronium molecules in the solution. So we're gonna attack it with water. Cool. Let's attack it with water. So I'm going to attack this with water. Attack it here. Boom. So this is our nucleophilic attack step. Okay, now what does this look like?
We've still got an extra
this
hydrogen, so we
correct?
need a proton transfer.
Exactly. Thank you. I was going to mention that. Okay, so how do we, if I was to draw this a little bit differently? How do we now get rid of that extra proton or that extra hydrogen?
Proton transfer to water.
Another water, because again, we keep remaking this hydronium. Right? So we just pick up another water molecule. Let's do it on top. Pick up another water molecule. Let me draw it like this. Boom, boom. And it's going to pick up this hydrogen. And now the electrons from here are going to be donated to oxygen. And now we have our final product. Yay. Was that easy? Are we good? Did that make sense? We did a proton transfer, which seemed like a nucleophilic attack because we were saturating the alkene. The alkene picked up a hydrogen in this first position rather than the second position, because if we did it in the second position, we would form an unstable primary carbocation. Since we formed the more stable secondary carbocation, it was able to do a rearrangement between bonds. We broke the cycle. We broke that ring between that carbon number 2 and that carbon number 5. That carbon in that bond in pink broke and reformed between 1 and 5. But this placed a positive charge at carbon number 2 because it originally didn't have implied hydrogens to begin with. It already had 4 groups. We nucleophilic attacked it with water because in our final structure, we have an alcohol group. And once we nucleophilic attacked it with water, we attached that water molecule, but we had to depronate it because it has a positive charge and it's a leaving group. It's not yet a hydroxyl group. So we depronated that with another water molecule and we ended up with our final product. Good? Is everybody good on this? Can I move on?
Yeah.
Yes.
Yeah? Okay, cool. All right. All right, now, all right, chirality. All right. Another chapter 5-ish question. This is going to be an easy question, or it should be easy. All right. If this was A, B, and C, and D, this is a multiple choice. Let's say A, B, C, D, and technically. By the way, what song lyric is this? Anybody? No? Cool. Y'all fell asleep? All right. How am I going about this? How do I know what chirality is? Anybody? I need to have a stereocenter, right? And these stereocenters shouldn't have what we call reflectional symmetry, right? Yes.
Yes.
Okay. And in the first compound, all right, first compound, is there a stereocenter? This is a tough Newman projection. Let me start off with the question. How many carbons are on this ring? Okay, so we have a front carbon, right? Front carbon, back carbon, represented by the circle. Same thing here. We have a front carbon, back carbon. So that's at least 4. What about here? This apex represents another carbon, and this apex represents another carbon. So how many carbons is that?
6.
6.
So this is technically the Newman projection of a 6-membered ring. And what, I mean, I can't do this on my iPad, but what you're looking at it is basically from this side. You're looking at it as if you're looking at it straight ahead. Okay, so this is, these two are these apex carbons. Like if this was front and this was back, this would be the front carbon, this would be the back carbon. Okay, and this is the carbon. So this is the carbon that's in the front on your left and on back on your left. And this is the carbon that's on front on your right. And this is the carbon that's in back on your right. So this is left and right. Okay. And so I'm going to highlight this back carbon in green on the right side. What's on that back carbon in green? Look at the structure.
Chlorine?
Chlorine. How many chlorines?
1.
Is it 1 chlorine?
2.
But
2.
look,
2.
two chlorines, right? There's
Which
2
of
chlorines
the-
on the back carbon.
It's 2
You see
chlorine
that?
because of the ones that are on the right
Yeah,
side.
Yeah, this is attached to the same carbon.
Okay.
You
All
see
right.
that?
Yeah.
Okay, cool. So is this a chiral molecule? Is this carbon in
No.
green, is that a stereocenter? No. So we can immediately eliminate answer A. Okay. How about, let's start with answer C first. Is there chirality in this molecule? And I'll show you a trick. The easiest trick is just to see if this is symmetrical with itself. Do we see symmetry here?
Yes.
Yes. Through this apex, if we drew this diagonally, this would be symmetrical, right? This is what we call a meso or meso compound. So we can also eliminate that. This is not a chiral center. All right. How about I'll do the example with D and then with B. How about with D? Is there symmetry? Is there symmetry with this molecule? Think about it this way. Can this single sigma bond rotate?
Yes.
It can, right? And if I was to rotate that, wouldn't this molecule look like this? And now is this a little bit more clear? Is there reflectional symmetry?
Yes.
Yes.
Exactly. So we can eliminate answer D. And the same thought process could be made with this compound. Essentially, all we need to do is rotate that sigma bond. And so we get something that looks like this, just to make it easy. I'm just going to draw it out. Right? And there's also reflectional symmetry. Okay? So we're left with answer E. But why couldn't we rotate this molecule? So we know E is obviously the right choice.
It doesn't have any single sigma bonds.
It does. This is. Are you going to tell me that this is not a single?
Well, I mean,
sigma
there's two of them.
bond? Yeah. So I mean, there's two sigma bonds. I mean, the same thing was here. There was a sigma bond here. There's a sigma bond here.
Yeah. All right.
The reason for that?
Is it because it's a chain?
No, these are chains. These are also chains. These are also chains. That's not the reason. Think about it this way. Is this chain, or rather, it's not a chain. It's a, if you like it, then you should have put a
Ring, sorry.
ring. It's a ring. And can we manipulate this ring so that we can switch the configuration of one of these hydroxyl groups? The only thing we can do is basically horizontally flip it. But if we horizontally flip this,
It would be similar.
it would be similar. And is there symmetry here? Can you just fold this up in a piece of paper and have the exact same thing on either side?
No, because one would be one of the alcohols would be in the back and one would be in front.
Exactly. So you couldn't just simply divide this in half and fold it up. There's no C2 symmetry. There's no reflectional symmetry in this molecule. So answer E is the only one that would be chiral. Okay? So look out for that. Look out. The point of this question is look out for reflectional symmetry. Okay?
I have a question.
Yes, ma'am.
So the ones that do give reflectional symmetry, that's how you know it's not chiral at all?
Yes, exactly.
All right.
Because you saw here basically is that we had chiral centers, right? But
Right.
because it has reflectional symmetry, it's not a chiral molecule.
Okay, got it.
Got it? All those
Yep.
other compounds are achiral. All right. Cool. All right. What about, all right, does anybody know the song? I'd be very surprised if you do. I'll actually give you bonus points. I'll give you extra credit if you know what this lyric to what this song is. No, cool. All right, doesn't matter. I was interested, but all right, what is how do we start naming this? How would we go about naming this? Anybody at all?
Did you identify the parent chain?
Yes. Where do we start from? Left, right, top, middle?
Right.
So 1, 2, 3, 4. Am I going up or am I going down?
Isn't it
Does it-
gonna be the same thing?
It doesn't matter
Okay.
exactly. So 5 and 6. Cool. So carbon number 2, this substituent would be a 2-chloral group, right? Wait, did we learn alkyl halides and things of that nature? Like, did he explain that to you?
Yes.
Okay, cool. All right, how about carbon number 3? This would be a 3 bromo, right? Okay, and there's 2 ways you could, what about this substituent? There's 2 ways you could name this. This could be either 4, and depends on if you want to do isopropyl, or how else could you name this?
1-methyl ethyl.
Is it just, okay, so is 1, 2, but you're forgetting the 4, right? So before 1, put this in a parentheses, 1-methyl ethyl, right? 1-methyl ethyl. All right. And lastly, on number 5, 5-methyl, right? So if I was to arrange this, and this is how long? 6, right? So it's a hexane. Cool. So how would I arrange these in alphabetical order? What am I looking at? I'm looking at B, I'm looking at C, I'm looking at M, and what about in this complex substituent? If I was to name it with its common name, I would be using I, right? But in this class, we're not going to be using I. I mean, in future classes, you may be using isopropyl, but in this class, we're going to be using the more easier version of this. We're going to be using E. Okay, so all you need to do is rearrange this such that you have 3 bromo, 2 chloral. What is this? What's next? 4 1-methyl ethyl, and 5-methyl hexane. Okay, this is your name. This is the name. All right. Now here, this is a little bit more complex. These answers are incorrect. Somebody tried to name this structure, and here's the tricky part. I don't give you the structure. So somehow I need to understand why this structure is incorrect, or why the name of the structure is incorrect. So we automatically know that we have 8 carbons, right? So if we have 8 carbons, let me draw an 8-carbon chain. So this is 1. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's an 8-carbon chain, right? And they're saying, okay, this is weird. So if I was to 1, 2, 3, 4, 5, 6, 7, 8, what they're saying is that I have a bromo, and it doesn't matter, I can, give it stereochemistry or not. I have a bromo on number 4, and I have a chloral on number 7. What's wrong with this name? With 4 bromo, 7 chloral octane?
Is it the numbering of the
The
carbon?
number.
Yes, exactly. So what's wrong with it is just the numbering. So the correct numbering would go from right to left. So now what would this technically be? 1, 2, 3, 4, 5, 6, 7, 8. So what is this compound called?
5-bromo 2-chloro octane.
Done. Easy. Not too bad, right? How about with the second one? What's wrong with the second one? So the second one, big hint, it's a cyclohexane. All right. And doesn't matter where I put this, but it's saying that I have at 5, I have a chloral. And at 6, I have a chloral. So same thing, right? If this was named correctly, I would have to number these differently, right? So I would number them such that the highest priority group would be 1, 2, 3, 4, 5, 6. All right. So what's the proper name of this? One, 2.
Chirality.
Chloral cyclo X. Easy. You're gonna get a naming question. All you have to do is make sure that you find the longest parent chain, and that parent chain has to be numbered such that you give priority to the lowest locant to the highest priority group. And then you just make sure that you put it in alphabetical order and that you name all the substituents correctly. Okay. All right. All right. This is just a quick
Are you
stability.
can you just go
Excuse
back
me?
to the last question I just did? Yeah.
This one?
Yeah. I'm just
Screenshot. All right.
okay.
Now, all right. Okay. So, all right. Well, this is a little Wayne song, but I didn't expect you guys to know this. All I want to talk about here is stability. And I'm sure you guys saw stability in class, but we're going to talk about stability in 2 forms, in bicyclos and in regular alkenes. So let me just draw a couple alkenes. If I had this alkene, if I had this alkene, if I had just this alkene, and if I had, I don't know, this alkene. Okay. And these are hydrogens on this third one.
the song is by Lil Wayne. Is it Steady Mobbin?
Yeah, we've used
just put the-
stability mobbing. Yeah. Okay. So A, B, C, and D. Which one is most stable?
D.
D.
Okay, D, right. So an increasing stability. Which one would be least stable?
C.
C. Okay. Next.
A.
There you go. All right. You guys are pros. I don't know why. Okay, cool. Easy enough. But I'm not sure if you guys know how to determine stability in bicycles. So let me draw. This may not come up on your exam, but I think it's valuable. It should be mentioned. So how about if I did, for example, let's draw a couple. So if I did this bicyclo, how many carbons? Let's do 2 carbons. This bicyclo, let's put an alkene here. How about let's do this bicyclo. This bicyclo. Yep, that's ugly. Let's try that again. That's better. How about this bicyclo? And actually, let me draw 2 more. Let's make this smaller. How do you make this small? Oh, nice. Let's draw this bicyclo. This one right here. one more. This bicycle. This bicycle. All right. Same process. B, C, or D. And in this case, I just want you to think which one is most and least stable. What do you guys think?
I think B is least stable.
Yes, correct. B is least stable. Least stable. What about most stable?
D.
Why do you say D?
It's in the tertiary position for both sides.
Right. So you would think because it has one group here, another group here, another group here, and another group here, that's similar to D, right? With 4 groups. However, bicycles are a little bit different, where stability does not increase if one of the substituents is a bridgehead carbon. So since this in pink is a bridgehead carbon, we don't count that. Do you see what I'm saying? Like, it's a small little, like, footnote in your textbook, but you wouldn't count this as more stable because you're not counting the bridgehead carbon. So this is almost a trick question.
I think that's what I was thinking of earlier when I was confused about the chirality center.
Yeah. So now that only has, essentially would consider that 2 groups. And the other, so C would be the one that has 1, 2, 3. Do you see what I'm saying? Like at that alkene,
Yeah, I see it.
not a bridgehead carbon. You see what I'm saying? But here, this is a bridgehead carbon. So C
is most stable. And then
stable.
D and then A.
Yes, exactly. But here we would just ask you, because it's difficult to say which one is more stable between A and D. I would say D is a little bit more stable, but that'd be like half of like a magnitude. It wouldn't be that much. So let's see, how are we on time? 11:45, and we don't have that many more questions. I could finish the rest of these questions on Sunday along with another exam review, but let's just finish off here, okay? We'll finish off with these last 2 questions because we only have 15 minutes left. All right, so, okay, what's the song from? Ground Control to Major Prod. Oh, please, someone, please surprise me. Tell me that you guys know the song. Or who's it by? No? Damn. All right. Homework, look up Space Oddity by
I was just gonna say that.
Yeah, this is Ground Control to Tom. All right, but anyways.
Hey, was that a Juice WRLD song earlier? I was thinking like I knew the melody, but I didn't know the name of the song.
No, this is Lil Wayne.
No, not the before that.
Shawty, what your name is? No, this is Kurt Cobain's. But yeah, if you guys can name all those songs and email to me, I'll tell Eric to give you, extra points on your, mechanism question. I'm just kidding. That's not fair. But, I'd like you more, and I'll probably give you more help. Kidding. So, all right. What's the first step? We have hydronium and water. What is this? Is this SN1? Is this SN2? What's going on? Think about what we just did with the mechanisms. What did we do? we saturated that alkene, right? And we saturated that alkene at this position, at the secondary position instead of the primary position, right? So if we're saturating that alkene, because nucleophiles are a good source of electron density, right? We would have a structure that first looks like this, right? That hydrogen is placed here, but I'm not going to show that hydrogen just to not confuse you guys. So that, all right, that secondary carbocation is placed. What kind of reaction would this be? Just this first step. This first
Proton
step.
transfer?
Yes, mechanistically, this would be a proton transfer, but is this SN1, SN2, E1, E2? There's two steps. So is this SN1 or SN2?
SN1.
SN1, correct. And now we have something which we call, I'm going to put this carbon now in gray. This carbon is now, or technically this methyl, is now moving here. This is what we call a methyl shift, right? This methyl shift now produces this molecule. And why is this molecule better? Why is this molecule better? Why is this molecule better?
Because tertiary carbocations are more stable.
Exactly. It's a tertiary carbocation. Correct. Now, I'm not done. I'm still on step one. But now I have a primary carbocation, right? And you don't, like, for these questions, all you have to do is draw the major product. Okay? You don't have to do all these steps mechanistically. But I'm showing you just for the sake of, like, understanding. So I have water molecule is going to attack this position, right? This is a nucleophilic attack. Once this attacks, what do we get? We get something that looks like this. Correct? Something that looks like this. And then we depronate it, right, with another water molecule. I'm not going to show that, but we're going to depronate that. And then we end up with something that looks like this. That is our first product. This is the first product. Okay? So it's something that looks like this. How about once we react this with HBr? What's going to happen? HBr with this, you know, alcohol.
Is that gonna be a nucleophile attack?
Yes, but tell me what kind of reaction. Is this SN1, SN2?
SN2.
Is it SN2? Are you saying that bromine is just attacking here? Is this a good leaving group?
No, it's not yet. It needs the hydrogen.
Yes, exactly. So what, and let me draw this a different way. So what's happening first is that this water molecule is being pronated first. Okay? That makes it into a good leaving group. This is what we call, this first step is a proton transfer, right? It makes a good leaving group. Water is a good leaving group, right? And what's left over here is a negatively charged bromine anion. So now that negatively charged bromine anion can now nucleophilic attack at this position and kick water out. Do we all see that? This is a nucleophilic attack. This next step is a nucleophilic attack. So now you have bromine now attacking and basically replacing the hydroxyl group. That is our second product. Our second product is this. Okay. And now, last step, what do we call this? Is this
Base.
What kind of base?
Strong base.
Strong base. What else? Size wise.
Strong. Small.
This is a small base. This is methoxide. You may see it written as like this over something like this, or just a simple CH3O minus over methanol, because methanol is basically the solvent. All right, so we're treating this now with a small base. What's happening with the small base? What am I forming?
Alkene.
Okay, where am I forming that alkene? And what kind of alkene?
A Zaitsev.
Zaitsev alkene. Yes, ma'am. And where would the Zaitsev alkene be? Would it be here? Would it be here? Or would it be here?
The middle one.
This one?
Yeah.
This one? Or this one?
The first one you pointed at.
So we have an argument. We have middle one or
No.
so okay. Is it this alkene? Is it this alkene? Or is it this alkene? Is it A, B, or C?
B and C are both Zaitsev.
Okay, but
But which one is more? Is C? Is the most,
exactly.
right? Yeah.
Zaitsev means the most substituted. So if something is most, there can only be one, right? So the most substituted would be C. Also, because you can pull hydrogen. You guys are right. You could pull technically a hydrogen from here. You could pull a hydrogen from here, or you could pull a hydrogen from here. They're all anti-periplanar. But what the correct answer is pulling it from the right side. And so these electrons now donate here and kick out this bromine group. That's what forms C. And that's your correct answer. So I'm going to erase A and B for now and show you that you make the most substituted Zaitsev alkene. Okay, and that's your final product. This is your final product, or your major final product. So that's what, after all this, you made this molecule. After these three reactions, you made this molecule, okay? And we're gonna give you a couple of these major product questions. And this is really testing you on chapter 7 and chapter 8. Do you understand mechanistically what's happening, whether this is SN1, SN2, E1, E2, and also, because this was an E2 reaction, right? This was a concerted step. This was an E2 reaction. And also we're testing you if you understand what reagents do to, alkyl halides or alkenes. So basically the takeaway here is know mechanistically what's happening, whether there's rearrangement or not, or there's some kind of inversion in stereochemistry. It didn't matter in this case if I drew stereochemistry or not. That wasn't really important. What's technically important is knowing whether it's an SN1 or SN2 reaction, or if it's an E1 and E2 reaction, and what all of these mean, what's going on. Okay. I'll leave this question for next time. for Sunday. And so we'll do this. Ozonolysis. A little bit of synthesis and a little bit more mechanism. So I'll see you guys 6 p.m. on Sunday. It's the same link as always, and we'll review more questions for the exam. If you didn't get to watch all of this, or if you joined late, please watch the recording. I strongly just suggest that you guys do the skill builder questions, do some of the end of the chapter questions, and please watch this recording or come to recitation or the exam review on Sunday. Okay? Does anybody have any other questions? Are you guys good?
This will be up today by like an afternoon, or I mean right now it's afternoon.
It's weird because you have to, the way this processes, it takes like an hour, like for every hour it takes like a secondary hour or something.
Okay.
So it should be up by like 3 o'clock. Since
Okay,
this
no
was
problem.
2 hours at 4, yeah, it would be up by like 3 or 4. Okay.
Okay. Thank you so much.
Okay. Anybody else? Speak now or forever hold your peace.
The exam is on Tuesday, right?
Exam's on Tuesday, same time, 9 a.m.
Okay, thank you.
Okay. Anybody
Thank you.
else?
Bye.
Nope. Okay. I'm gonna stop recording. Sure. You guys all have a good day. Good luck. And yeah. All right. See you guys.